Thank you, Scott, for the invitation and introduction. So I will first preface by saying that this is actually kind of like a difficult talk because, when I heard from you, I understand, I think a majority of the WEI audience are working on biomass, energy-related topics. So I'm trying to actually bridge what we do with what you guys do. And then I actually got quite ambitious. Actually, I enclosed several different topics in my group into one talk. So this is actually the first time I tried to do all this broad combination, okay? But then as the time get closer, I realized this actually there's a bit of undergrad class component as well, which make it even more challenging. So just like in the last 2 hours, I add a few more general slides. So the idea here is really just to convey some general ideas instead of going to a lot of nitty-gritty details of what we do. So basically, I'm going to actually articulate a few big ideas and general visions, and then illustrate them with some of the research we do. Hopefully, they make some sense at the end. But if it doesn't, I apologize beforehand. This is the first time I give this talk in this session. Okay. All right. So as I said, I will talk about electrochemical production of value-added chemicals. This is a part that's speaking to the WEI, the biomass, researchers, and storing solar energy, in solar fuel batteries. Okay, so that's the title, right? So I want to actually preface by saying that I hope you agree with me, but the fact of the matter is such that the renewable energy revolution is happening now. Okay, it's not a something for the future. It's actually happening as we speak. Okay, so this is actually a picture taken from some DOE report where basically we probably noticed actually that wind energy are growing very quickly. Solar PV are growing quickly. I mean, we're seeing increasing deployment of electrical vehicles, and then now on the energy saving front, LEDs and many other energy technologies are rapidly being deployed. Right. So this is actually in fact happening as we speak. Part of that reason is because a lot of the technology that we heard about, like PV, solar cells, and wind energy, their price has been dropping quite quickly over the last couple of decades. In fact, in many cases, they're dropping faster than we anticipated. They're dropping faster than we actually ever imagined. Okay, for example, this is actually, you can look at some of this. I guess LED, we already see it, right? We already have using this in our homes. But then for PV particularly, utility PV, this is actually the big ones for the utility companies. Distributed PVs, these are things that you put on your rooftops. They're dropping in in a very fast rate. They actually were about half of the price in less than about 7 to 8 years in the last decade or so. Right. In fact, actually, about 6, 7 years ago, DOE convened a panel and made a target called Sunshot target. Meaning that, kind of like moonshot, they're trying to aim to make the solar cell prices to be lower by about, to about $1 per watt in terms of the output. They actually thought, we'll be happy we get there by 2020. But in reality, this target was reached last year, purely just because of the fact that people are learning how to manufacture the solar cells in a larger scale. They're getting the price cheaper. And I think part of it is actually that the Chinese government decided to subsidize the whole humanity to convert the solar PV really fast. You might have heard about that part as well, right? So basically, the price were dropping a lot faster than we thought, to the point actually that, in fact, last year, several states in the US, particularly the state with more sunshine like Arizona and California, if you build a solar power plant and generate electricity out of the solar PV, and then compare to the price of electricity you generate from natural gas or fossil fuel burning power plants, you get the same price. So this will be what we call grid parity, right? So basically the price of getting the solar electricity from PV and the price of getting solar electricity from petroleum will be the same price, which obviously is a big deal, right? Then people will say, well, that we don't have to just do it because we want to help the environment, be more renewable. We do it because it makes sense. It's the right thing economically to do. Right. So in fact, that's actually part of the reason why the deployment were accelerating. And same thing with the wind power. I have traveled through some of the states west of us. South Dakota. You see, wind farms, on both sides of the highway. As far as you can see, right. So this is actually really happening at an accelerating pace. Right? So this is actually, a phenomenon. I think it's not. A lot of people will say it's not a question of if. It's a question of how fast. So we have already reached the point of no return. It's going to take off from this point. Okay. However, there's one problem. The problem is actually that a lot of these renewable electricities are intermittent. Okay, so we all know actually sun go down every night, and when cloud comes, we don't see sunshine, right? And wind might not be blowing all the time either, right? So actually this is a big problem. We actually going to have fluctuation of electricity supply if we keep deploying the renewable energy. Okay, in fact, in some European countries where wind power, maybe to some degree solar power are more dominant, like Denmark and Netherlands and Germany, we are at the point that the electrical grid are not very stable anymore. Okay, so they cannot deploy any further. The other thing with solar energy is that solar energy is a bit diffuse. They have low photon density, so per unit area, the energy we get is actually not that much. Okay, even though we have a lot of them, because we can actually have a large area, right? So basically, I will make a general statement saying that if we want to utilize solar energy and other renewable energy further, we do not just want efficient solar cells, but also we need to have a way to store this massive amount of energy efficiently and inexpensively. This is what we call grid level energy storage. So how do you store the energy at a level for grid, right? So in fact, there are some solutions, okay? And then there are actually so-called flywheels. You fly mechanical wheels and you basically store the energy in a mechanical rotation, and then you generate electricity back when you actually want to use them. In fact, the other one, this is actually probably the most dominant right now. This is actually about 90% or 95% right now. Pump water storage. You have a reservoir. When you have a lot of renewable electricity, you pump the water up. When you want to use it later, you let it come down and regenerate the electricity. In fact, there's actually I haven't been there, but I've seen plenty of pictures of this. On the eastern shore of Lake Michigan, there's this lake called Larkington Pump Storage Power Plant. Basically, they pump the water from Lake Michigan up here, when the electricity is cheap, and then flow back when you come back. This is actually called Larkington unit. Okay. So how much energy you get out of this reservoir is called 1 unit of Larkington storage. Okay, so that's actually a way that people are using. Okay, and there are actually also you can think about using lithium batteries. Although I would say most people, not everyone, most people will imagine it's going to be very hard to build a scale of batteries enough to supply the level of storage for grid. Okay. And even though Elon Musk made a general statement, when Puerto Rico was hit by Hurricane Maria, he wanted to outfit Puerto Rico with, a new infrastructure with storage. But in reality, if he cannot build enough batteries for his, Model 3, I think it will take him a while to be able to build enough battery for Puerto Rico, right? So that's actually sort of generally how I think about it, right? So there's actually another approach of using so-called redox flow batteries, which we'll talk about later in my talk. But then from the other point of view, in a way, chemical energy, storing the energy in chemical fuels like hydrogen and hydrocarbon is in fact a way to actually keep a lot of energy, because chemical energy in general is very dense. Chemical bonds store a lot of energy, probably only behind the nuclear energy, right? So compared to mechanical or water or gravity, these are much more energy dense than the other approach you have, right? So this is actually basically in a way being able to do chemical conversions and making chemicals and making fuels using renewable electricity is in fact in a way an argument to be made about storing energy, right? So that actually brings the next idea, which is that now with the increasingly available inexpensive renewable electricity, you can think about a sustainable production of fuels and chemicals using electricity now. Okay, the equation have kind of switched a little bit, because traditionally you always think about electricity as being expensive because your electricity usually comes from burning fossil fuels. So if you do a general chemical conversion, if you talk to a typical chemical engineer, my colleague E. Kermans will always say to me, no way, you cannot compete with me if I do the best chemical reaction I can do. There's no way you use electricity you can beat my efficiency. I agree with that general statement, but the point is that in the limited cases where you have abundant renewable electricity, when there are excess of them, you cannot utilize very well. If you use that to generate fuels and chemicals, you do something interesting, right? And then you actually have a way of storing that energy in a way into those fuels, right? So this is actually taken, this is the vision picture taken from a review published about a year and a half ago, where they're basically saying, you can use electricity to do electrocatalysis and photoelectrochemistry to take water to split into hydrogen, to take CO2 and reduce them to hydrocarbon, even maybe taking ammonia, nitrogen to generate ammonia, the Haber-Bosch process, which is arguably the most important contribution chemists made to the humanity. And if you can do all of those using electricity, then you have a different way of imagining how you make fuels and how you make chemicals and how you utilize them. You can burn them the fuel cell, you can store them, you can transport them, and also you can maybe convert chemicals from biomass into actually more expensive chemicals and so on and so forth. Right? That's sort of the general vision, right? From the point of view of using electricity to do additional chemistry to do fuels and chemicals, right? Of course, you can introduce a second layer of idea, which is that you can go directly from solar energy to actually generate those fuels, which is what people call photoelectrochemical or chemical energy conversion. And in this case, for example, we're using the example of water splitting to illustrate this. Okay, so as you know, water is a very common chemical, very clean, right? Water. We use it everywhere. If you split up into hydrogen and oxygen, obviously, hydrogen is a fuel. It contains quite a bit of energy in the hydrogen-hydrogen bonds. Okay, you need about 1.23 volts of voltage to split up the two components into hydrogen and oxygen. And then to do that, you need solar energy. Typically, people use a solar semiconductor and excite the electron holes through them, and then separate them and use the electron to do catalysis to reduce the proton to hydrogen, the so-called HER, hydrogen evolution catalysis. On this side, you can do oxygen, OER, to oxidize the water to generate oxygen, right? So you need semiconductors, you need catalysts, right? So to generate a PEC solar cell, you need all of these components, right? So of course, as I said in the last page, you might not have to do a direct PEC conversion. You can just take the electricity and hook up with an electrolyzer, take electricity from a PV cell, hook up to the electrolyzer, where you mostly just have HER and OER catalysts, and you can do the same thing, right? So basically, in the first part of my talk, I will show you a few examples my group have worked on over the last 6-7 years of doing HER catalysts and OER catalysts. And then we're going to go broad to think about more broader chemical conversions, and then finally I'll switch into a full batteries. Okay, so actually, before I go in that, I will introduce another set of ideas, which is that to do a lot of those, I think it's important to think about materials beyond the typical material we've been using so far, because these are large-scale challenges. You wish to use materials that are really abundant and really inexpensive in the Earth's crust, right? So this is actually an abundance chart of the elements in the Earth's crust. Before we can figure out to do space travel efficiently and cheaply, this is probably what we will have to be working with for a while. And a lot of the common solar cell materials, and a lot of the catalysts actually you use, like platinum, palladium, are actually quite rare in this, in this picture. It's actually a large scale, by the way. Okay, so you rather want to use something from this group, or maybe at least something from this group that actually will allow you to do this, so that if you are trying to scale up this technology, you are not going to be limited by the availability of materials. So the other way I like to say is actually that you don't want to turn the dependence on petroleum into the dependence on platinum or lithium or something else, right? Which you're not doing much in that regard. Okay. All right. So let's actually go into the first problem, HER, hydrogen evolution, right? This is actually arguably a very simple reaction. You simply are just taking two protons and actually convert it to hydrogen. Okay. So this is actually, in fact, what defines the thermodynamic scale of the electrochemical energy level 0, right? So the theoretically it should happen at 0. Energy zero potential for the electrochemical energy scale. And the traditional catalyst for this is actually the noble metals like platinum, palladium, and so on and so forth, right? And the typical way people think about doing this is actually to think about designing a catalyst where you have a binding energy of the intermediate, which is the hydrogen atom, to the catalyst at the near thermal neutral. Basically, it's really easy to bind it on. It's really to get it off. So when you are at that location, usually the catalyst is really efficient. And platinum is actually just like that. This is actually what people call volcano plot. You plot some metrics of performance as a function of binding energy. You can see these actually are sitting right on top of the tip of the volcano, the peak of the volcano plot, right? So the challenge here is actually that can you actually find other catalysts that actually it doesn't contain a noble metal, very expensive to do this, right? So there are actually other catalysts you can do in energy. Well, I'm not going to do this here today, right? So now the general argument I made and the observation I have found in the last few years is that really there is a general trend of looking at the periodic table and the broader material classes over the last 10 years or so. All of the electrocatalysis topics, right? So this is in fact, a very easy to understand idea from a solid state chemist perspective. I was trained as a solid state chemist, so I think about periodic table a lot. At the beginning, people used the really active and very stable, noble metals like platinum, palladium. But then they start to look at non-metallic alloys, and then you start to look at compounds like sulfide, a simple compound like binary sulfide, molysulfide, the layer ones, and the non-layer ones, going to nitride, many other different compounds, right? So the general trend of the electrocatalysis community has been an expanding trend where you go from simpler to more complex materials, where you can begin to learn how to design the catalyst, tune them to improve their performance, and actually in that process improve the performance and reduce the cost, because you actually will move away from using the metals in this group, right? So that's actually the general idea, right? So particularly for us, we made good contributions to two classes of materials. One class is called layer materials of catalyst. So this actually she started about 10 years ago when people like Jan Nosal from Stanford and his colleagues actually theoretically predicted actually that molysulfide, a layer compound, could be a reasonable catalyst for HER reaction, the hydrogen aluminum reaction. These compounds are layer structures, just like graphene you know about. There's van der Waals interaction between layers, and there's actually covalent sheets in the same layer. And very quickly, experimentally, they realized actually that usually the catalytic activity on the edges of these 2D sheets are better than the center, which makes sense from a simple chemical argument. You have unsatisfied bonds on the edges. You have much inert basal planes because of the van der Waals gaps between them. So this is actually sort of what people were thinking about 6, 7, 8 years ago. A lot of people are working on increasing the number of edges, trying to improve the catalyst, and so on and so forth, right? So the unique contribution we made is actually that about 6 years ago, we discovered that by taking these layer compounds, making the nanostructures, we're going to actually make good catalysts. But more importantly, by taking those layer compounds with metal layers, if you actually intercalate lithium in between these layer sheets and then exfoliate them into single sheets, you can dramatically enhance the activity for the HER reaction, right? So what happens in this intercalation is actually that not only you open them up and get more surface area, which you do, it's part of actually the gain here, but that's not the most important gain. The most important gain is that lithium intercalation and isolation reaction basically putting more electron into the system, so you reduce the whole system to a different electronic state, to the point actually that even the crystal structure of this material has switched. Originally, you start out with the so-called 2H molysulfide, where the molybdenum is sitting in the trigonoprismatic environment. After you do the conversion, it's actually in the so-called 1T molysulfide, where the molybdenum is sitting in the alkyl environment of sulfur. Okay, so this 1T molysulfide is actually completely metallic. It's actually much more conductive than actually the one you have before. So overall, you actually get a very dramatic enhancement of the catalytic activity and performance. Right. So in fact, at the time this was published, this is actually one of the best pure molysulfide catalysts out there. Not only the performance is very good, we also learned actually that the so-called Tafel slope, basically the log, semi-log curve slope of this reaction is actually already different, which tells you something about the fact that these catalysts actually operate in a very different mechanism as actually the traditional one you have. Right. So basically, this is actually sort of our entry point in doing this. I'll just give you a couple more examples. So in the second step we did, we actually also further enhance this catalyst by making a lot of holes in that 1T sheets. You can say, well, 1T, is that still only active on the edges? You can ask that question if you have more holes compared to less holes. We can compare wholly 1T with no holes and see if they're different or not. Turns out when we did that, actually we did this using a very bizarre procedure, very crazy procedure. We actually dissolved lithium into liquid ammonia, and then use that to intercalate and exfoliate the molysulfide. You actually drill a lot of holes in it, but not only you drill holes, you actually make a lot of defects. Turns out a lot of this actually make the performance actually quite a bit higher. But what we learned in the end is that in the end, it was a lot more complicated than we like. In the end, from this work, we learned that the phase of the controlling the phase of the material is actually probably the most important thing to give you performance. Vacancy is probably the second most important. In fact, in the end, probably the edges is the least important in this exercise. But still help, right? So when you have something with more edges, it's always better than having no edges. But just having edges, if you do not actually understand the phase and the vacancy very well, don't do very well. Right? So that's sort of, I think, some nugget of what we're doing in the molysulfide. I'll just now show you a few examples we do to actually build a solar cell. I think I probably need to be a bit more brief So we actually also learned how to actually build amorphous molysulfide catalyst, kind of similar to what we talked about. But now in this case, with amorphous coating, we can easily build solar devices. Okay, before we do that, we realize there's something really interesting about this amorphous compound. The interesting thing about them is actually that they're transparent. Okay, so we actually coat this amorphous molysulfide chloride on a piece of glass next to a blank piece of glass. You barely can tell there's color here, right? There's a bit of tint, but not so much. This is actually the analogous molycyanide chloride. Okay, turns out this is actually quite important because when you actually try to put a catalyst in the integrated solar photoelectric system, you do not just need a good catalyst, but also need a good transparent catalyst because these are going to be on top of the semiconductor. You don't want them to block the light that actually will go through that to actually go to the semiconductor. Right? So basically, we learned actually that this is actually another criterion you want to have to design good catalysts, but also you have to have good semiconductor as well. So in this paper, we also learned how to actually use nice silicon PN junctions with a pyramid structure to allow you to harvest the sunlight really efficiently, because all these pyramid allow you to scatter light really efficiently and then take light in without losing them. So we got those solar cells from my collaborator, Professor Zhihao He from KAUST, who is an electrical engineer, who are really good at, who is really good at building solar cells and so on and so forth. We got those cells and we coat this molysulfide chloride on it, and then we're able to actually do direct solar to hydrogen generation, for these systems, right? So in this case, in fact, I will not go into too much here. Just say we got about 6% efficiency, which is not the highest, but now we only have silicon and very inexpensive catalysts and semiconductors, right? But then the interesting thing about this is that in this particular case, actually on the photocurrent point of view, the part that how much photocurrent density you generate out of the device, you actually can do better than if you use platinum. The reason is because platinum will block some light, and this one do not block light, right? So this is basically the bit of fun we have building, actual solar field generation device out of the catalyst, right? So that's actually sort of one type of family, molysulfide. So we also actually work on another type of family called pyrite family. So the reason we go in there was actually while we were working on molysulfide, we realized a typical pyrite structure like cobalt sulfide have some of the very similar structural features as you see in the molysulfide compounds. We naturally asked the question, can this possibly be HDR catalyst too? Okay. In fact, these are very common compounds. It's just that people haven't looked, right? So we looked. And actually, they're actually quite good. Actually, the cobalt sulfide is very good, but then we were able to actually modify it further. And in this case, what we did is actually that we asked the question, based on what we learned from the other cases, if you tune the electronic structure, can you actually improve the catalysis? We tuned the electronic structure by substituting the sulfur with the phosphorus. Is actually one left to the sulfur in the periodic table, you're going to get less electron activity. Then you actually can get this compound called CoPS, which is actually also a known compound. It's a mineral you can find in the natural world. There are about 3 papers on it. People who actually will look at it. And then we made the compound. Actually, also in this case, we actually got my colleague J.R. Schmidt, who can do DFT calculation on catalyst. Actually, he also seemed to see that based on the theoretical calculation, this will be a good catalyst, probably better than cobalt sulfide as well. Right? So we made nanostructured CoPS into high surface area structures, and we measured it. Actually, we're very happy to see that, in fact, this actually performed very well. In fact, at the time it was published, this was the most active, acidic, HDR catalyst that doesn't contain noble metals. Actually, I'm very happy. I got about 30 seconds of fame in the Wisconsin Public Radio when this paper was published. Chuck Kimball, actually someone you probably have heard over the radio all the time, interview us, and we got about 30-second clip. One of my colleagues even heard about it on, while he was driving. Yeah. But anyway, so that's sort of the best HDR catalyst we made over the years. Right. So now with this kind of catalyst, we can also build very good PEC solar cells. Okay, so we can actually, in this case, coat a thin layer of this on the same PN pyramid you saw on the page before. And then in this case, interestingly, the efficiency is actually less than what I showed a moment ago. The reason is because even though this was a better catalyst than the other one, this case, actually the CoPS does take up sunlight. So you cannot have too much of them. If you have too much, the efficiency will drop. You can have too little because you don't have enough catalyst. So you actually, play, the game right. You have the optimum. You have about 5%, right? But nonetheless, it's actually again a fairly efficient, completely abundant, completely inexpensive, solar PEC devices. Okay, so I think that's actually the HDR side. So I'll just actually quickly say we're also working on the rationale of generating OERs. Okay. and doing the other side, generating oxygen, right? So this is actually, in fact, a much more complex reaction. I would say, I'm pretty much done with HCR because, if you can get 50 millivolts, only about 20 millimoles less than platinum. I guess I forgot to emphasize, we're really, getting very close to platinum, right? If you're only that close to platinum, there's not much more you can get, really, right? So, basically, we're now I think the challenge on this side is actually a lot harder because actually you have full electrons, right? The variable interaction is far more complex. And the material you can work with is, in fact, a little bit more limited because, these are mostly oxide and hydroxide that will be stable in the oxidative environment for the OER. And some detail I won't go into. So particularly for this one, we've been working on this class of material called layered double hydroxide. These are minerals or artificial materials with layer crystal structures, kind of like the molysulfide I showed you. But the difference is that in the layer, you can have two different metals, a +2 metal and +3 metal. So basically, you can take two elements or even more elements from the periodic table and do all kind of different combinations. And a lot of very good catalysts are found in these families. Actually, in fact, some of them are already beating the classical benchmark of iridium oxide and ruthenium oxide and stuff like that. And people are still hoping to actually do better. In fact, I didn't know Shannon will be here. We're even working on this together. But I skipped that slide. I'll just say, for example, recently we're trying to learn actually how to design better ones, and we actually go beyond the typical one that people maybe thought, usually based on nickel and iron. We actually found out that mixing in chromium into that mixture by having a trimetallic, catalyst, you actually can improve upon nickel iron, LDH, which is traditionally considered as a benchmark for this kind of OER catalyst, right? So we moved, the samples maybe about 50 millimoles, 40 to 50 millimoles. Okay, not a whole lot, but it was actually better than what people had before, right? So still actually a lot of ongoing activity here, but now we're using this catalyst to do other reactions. This is actually why I have to talk about this, because this is actually the entry point to talk about the fuel generation part, the chemical generation part, right? Which is really that. Now I'm switching gears completely. Now instead of doing small molecules of hydrogen and oxygen, now I'm thinking about generating more valuable chemicals. Okay, so and this is actually something that I think the people working on bioenergy are quite familiar with, right? So there are a lot of feedstocks you get from biomass, right? So HMF, glycerols, glucose, lactose, and so on and so forth. And they are obviously valuable, but then if you can convert them to something even more valuable by oxidizing them a little bit further, but do it in a controllable way, then you generate additional value. And you will now can potentially do this with electricity, right? Electricity from solar cells or electricity from windmills, right? In fact, again, if you argue compared to the chemical conversions of using what, say, Jim Dunasic and George Huber will usually do, putting a thermal reaction at 400 degrees and putting some catalyst in there, probably at a large plant scale, we will not be as efficient as they are in the short term. But the nice thing about these, electrochemical conversions is that you can do it in a distributed manner in a remote location. Let's say the farmer has a small device right by the windmills on his field, right? You don't have to transport all of these, inexpensive feedstocks, far away. You actually convert into a more expensive one, then you actually transport that, right? So that actually, there are certain scenarios actually that this might be interesting, okay? In fact, you can also turn this device around. These actually can also be fuel cell devices as well, right? You can put this in here and you can burn them completely into carbon dioxide. You can generate electricity. Of course, there's another subtle scenario where maybe you can oxidize them partially so that you generate some electricity, but then you still have the product of that oxidation to be something still valuable, right? So then that would be even more interesting. It's a fuel cell that actually produces useful chemicals, right? So these are actually potentially some of the scenarios you can do, right? Of course, you can also say, I can actually use the electricity and reduce the biomass and then into more clearly like a hydrocarbon, reduce it closer to a hydrocarbon, then you actually have more value in them as a fuel. Okay, so this is actually, in fact, what I really wanted to do at the beginning when I started to think about this. But then I would say over the last 3 years after I started to interact with Professor George Huber from Chem department, I began to realize a different way of thinking. So I think for chemical engineers, for them, the value of the product is far more important than how interesting it sounds like, right? It sounds like it's interesting you're producing hydrocarbon, you're producing fuels, but in reality, it's actually that before we actually finish up the petroleum in the ground, that will be very hard to compete with. you have always, a constant stream of low-cost petroleum and natural gas from digging. But then, to go from those petroleum to burn all the way to do the high-value-added chemicals, actually, you have to spend more energy and more time. So it's a lot better to compete on this end than that end. So basically, after working with him for a few years, I'm actually a lot more interested in doing oxidation instead of reduction, right? So that, I guess I probably went into a little more detail than I need. But anyway, so the idea is that can you do this kind of biomass molecule conversions using electrochemistry, right? So here are actually some list of the chemicals. I'm just reading up on this. I'm still new at this. These are 10 chemicals that people in the biomass community put out and saying these are the platform molecules. These are the molecules you can easily get access to when you actually use them to generate something else. So we started to look at this and do something with this, right? So the first thing we did is actually with George. Okay, we had a visiting postdoc, visiting scholar coming in with his own support. So for some reason we can never get this funded through UW 2020. We give up, but we're getting the work done already, so that's great. So we actually put the HMF in the electrochemical cell, and then we just use the same catalyst for OER reaction I just talked about a moment ago. In fact, it was almost the first one we tried. And we put HMF in it, put it on the anode side. And then basically you're actually oxidizing HMF into its acid, into different intermediate. And then on this side, oops, looks like it's dying, you're actually reducing the water into hydrogen. Okay, so I guess if you like hydrogen, you can even argue, well, we're still co-producing hydrogen, right? So on that side, it's useful. But at this stage, I feel probably the value in the chemical you generate on the anode side is actually probably more than the value you generate on the hydrogen side. Again, to produce a hydrogen and compete with using natural gas to generate hydrogen using the the very simple reactions, I think it's called the syngas reaction, right? That will be very hard to compete with them in the short term, right? But now on this side, to generate things like DCA, this diacid, actually, it turns out there are a lot of interest in this, and we're putting some value here, right? Basically, the first one we tried seemed to work reasonably well. Okay, so it's actually nickel ion LDH is the same one we use for the OER reactions. Actually, you can see that certainly it's a lot easier than generating hydrogen because you have organics that you want to oxidize, and you can actually convert them in about a time of a few hours. They actually will completely go into DCA, right? In fact, they actually do not go further. They just stop there. And if you like this product, you can say the activity is actually quantitative is actually almost 100%, right? So that's actually the first thing we did. So now also we're actually starting to look at glycerols. Okay, in fact, I like this better because it's even simpler. It's a smaller molecule. So glycerol turns out, people I read, I don't know enough, but I'm reading that people say that glycerol is actually a byproduct of a bio-oil refinery. And so there's actually quite a bit of supply of glycerol out there, and actually a lot of people, not a lot of use for it. Okay, so people like to maybe oxidize them into some other chemicals, and you actually might use it to do something else more interesting, right? So this is actually again done by a visiting student. So over the last year or so, we actually discovered a whole bunch of so-called oxide spin-out catalysts. Okay, these are ternary oxide. So 2 metals in it. Usually always with cobalt, and we try a different A metal. Actually, this is dying now. Probably should try a new one. Okay. This is a little pointer. Okay.
Otherwise, you can use this pointer stick too.
Maybe I'll use this one. Okay. I am not used to that. Okay. This is working.
Might have to take the USB out of there on the bottom there.
Okay. I can do both. It's okay. Yeah. This saves the trouble. Okay. It's not so much better, but okay. All right. So we can put in these different spinel oxide. As you see, that we grow this directly on a piece of carbon paper. So basically, the thing we grew are directly a electrode. So this whole piece of paper with other catalysts on it are going to be deep into solution in the kind of style that you saw on the previous slide, like H cell you have here. It's actually not too much better. Okay. All right. Anyway, so and then you can see actually that as you actually add this, actually you're going to actually be a lot easier to generate these reaction going compared to you evolve oxygen. So this actually curve will be actually what you will do to evolve oxygen. And interestingly, actually there's some dependence on the metal. We're actually trying to figure out why these trends work the way they are. Right. So now also with this kind of, oh, it's really bad. Maybe I have to complete this. Okay. All right. So you can see actually it's okay. Yeah. Maybe I'll switch. Okay. Switch. Yeah. So if you really see this, actually, you actually do produce several different products. Okay, so in this case, I would say maybe you say unfortunately, we didn't keep it at a C3 or C2 stage. Okay, a majority of them, about 70% of them, going to formic acid, which is probably the least valuable of the three. But there are some glyceric acid or glycolic acid. Actually, of course, this is done in the alkali environment, so they're all turned into ions. And then there's a bit of oxalate, depends on what catalyst you use. There's one catalyst that will give you the oxalate as well, right? So we actually convert them into, again, other chemicals using electrochemistry, right? So the truth is that, in fact, these catalysts are not that efficient yet, okay? They're good in the sense such that they are really easy to make. They're very cheap to make. There are no, expensive metals, no platinum, no palladium. But in reality, if you look at the overall potential we have, where we still have a long way to go, but this is actually a good start, right? So this is actually sort of, I think the one direction we're interested in, we're increasingly looking at converting small organic molecules that might be biomass derived and try to use that to do something interesting. Oops, I'm not familiar with this one, okay. All right, so now another new direction we have on doing the electrochemical conversion is to try to generate H2O2, okay, hydrogen peroxide. Okay, so it turns out this is actually, in fact, probably the one that have maybe even more potential in the near term, because actually hydrogen peroxide is a valuable chemical. People are making it on the few million ton scale every year. But the problem is actually that the current way to make it is quite expensive and quite energy intensive. They use anthraquinone as a intermediate to generate a chemical. You have to use hydrogen, oxygen gas on both sides. So actually, it's actually quite expensive. But more importantly, because it's a strong oxidizer, hydrogen peroxide is quite expensive to ship because it's actually very hazardous. You don't want to ship this in a concentrated fashion because it will be explosive. It will be very corrosive. But if you don't ship it in a concentrated fashion, it's very expensive because you are just shipping water, right? So in a sense, this one has a better argument to be produced locally and used locally. Okay, so people in the water, in the paper industry, people in food industry, people in wastewater treatment, all use this. So if you can actually figure out a way to produce this, on demand locally in the distributed fashion using electrochemistry, then this actually will be something interesting, right? So basically, we've been working on developing new catalysts for this, okay, and actually a lot of people have tried this. The best catalyst before this was platinum mercury. So first of all, platinum, and then the second thing they have to put in to make that work well is actually mercury, which is actually not something sounds very fun. So we actually discovered that there's the this compound of cobalt sulfide, the same one I mentioned a moment ago for OHR, turns out to be a pretty good catalyst for this. In this case, the challenge here is actually to twin the selectivity, because this is really the simple reaction of reducing oxygen into water and hydrogen peroxide. Reducing water is basically what people use in the fuel cell. Majority of people are trying to do this, make this oxygen reduction reaction into going to water to make fuel cell work. So we're kind of going sort of the the different way, right? So and actually it's rare to find the catalyst that's selectively going to the intermediate hydrogen peroxide. And this one actually was quite good. The selectivity is actually about 80%. Actually, we now have a new example that is actually approaching 100%, although the activity still can be improved, right? So this is actually again something we're really interested in, producing valuable chemicals using electrochemistry. Okay, so I think that actually probably is the first part. So now the second part, maybe this is just 10 minutes. I'm not going to actually articulate a different idea. Again, on the idea of utilizing and storing the solar energy, but now have a different train of thought. In this case, we're really trying to think about how can we supply the electricity really well, but going through chemical method. Okay, so how to do that? Okay, turns out, as I said, there is actually another way to store the energy on the grid level called redox flow batteries. Okay, so redox flow batteries are really just liquid batteries where you can actually have in-liquid electrolytes with chemicals in it, where the way of storing the energy is using electricity to react and turn over these couples to convert them between different oxidation states. So you can put the electrical energy into chemical energy, and then you can put them out in the tank. And then when you want to use electricity, you flow them back, and then you regenerate electricity. Right? So why is this actually potentially better for grid energy storage? The reason is because this is actually more scalable and very easy to actually make a large scale, right? Because you can imagine, if you want to have more storage, all you have to do is build a bigger tank. Okay, the power unit of this battery and the storage unit are separate. Okay, so this will not be useful for portable electronics like for your cell phones or for your laptops probably not useful for cars either, because then you have to deal with flowing liquid, you have to have pumps, you have many different components. But when you build large-scale devices, the benefit will actually show. Right? So basically, a lot of people actually believe in the long term, in the grand scheme of things, this will be far more promising for large-scale storage, for the utility scale, than lithium batteries and the traditional solid-state batteries that you're familiar with. Okay. In fact, this is actually again happening. This is commercially happening now. In fact, there's even a company in Wisconsin called Inthink, actually really strange, good name, outside of Milwaukee, that have been in existence for about 10, 15 years. They're actually starting to take off recently now. They're doing a version called zinc bromide battery, which is not the most popular one. The most popular one currently commercially being deployed are these so-called vanadium flow batteries. So, people are putting into megawatts units. There's actually a picture of that. It's like a tractor trailer kind of size of a flow battery. And in fact, I think actually sometime later this year, in the next few months, there's a unit in China that will be about 200 megawatts. Okay, so these are really happening. This is actually not fictional. This is really happening. Right? So now, of course, there are a lot of people working on full batteries. But now I have a new idea, which is actually that how about we think about combining or integrating the solar cells with a full battery reactor, so we can do one device where we can do both of them together. Right, so now this actually now come back to the idea of photoelectrochemistry that I talked about at the beginning, when I talk about water splitting and so on and so forth, right? Turns out there are two types of photoelectrochemical cells that people usually work on. The water splitting cells, actually I talk about generating hydrogen or generating hydrocarbon from carbon dioxide, or what you call photosynthetic cells, where you are using the electron hole you harvest out of the semiconductor to do chemistry, to change their chemical state, to use it to drive the fuels. There's another kind of solar cell called regenerative PEC liquid junction cell, where what you're doing is you actually put in a redox couple, which is a very fast and efficient, kinetically efficient couple. You use them to mediate between the semiconductors and then counter electrode to actually harvest the carriers and carry to the counter electrode to generate electricity. In fact, if you actually ever heard about dye-sensitive solar cell, DSSC, that's actually a type of regenerative solar cell. You are using, in that case, iodine iodide to harvest the holes from the dye-sensitized TL2. You actually put it on the counter electrode, you actually get electricity out. Right? So basically, this is actually what I want to use for this new idea, because you see, you also use a redox couple in this regenerative PEC cells. This couple can be the same couple as you use in the flow batteries. Okay? So then you can just build an integrated device and actually do this function directly, right? So I guess probably I don't need this slide. I'll just go into the slide directly. Okay, so now this is actually the thing we did first. We published a paper about 2 years ago. This is actually the basic idea, right? So now imagine if you have a solar cell. It's shown here. This is actually a piece of silicon solar cell, actually very similar to what we used before for PEC water splitting. You actually can then shine light on it. You can actually harvest electron holes. Okay, in this case, we're just doing electrons. Just focus on this side. You're reducing the AQDS into AQDS with hydrogen, and then you are actually doing some chemistry here, and then you can finish. When you finish charging this, you're basically charging up the redox couple. You are storing energy to it. When you finish this, you can just put it into the tank. Okay. And actually, of course, you can do similar things on the east electrode to use another couples. Okay, you can oxidize it and actually put in another tank. Then during this time, you're basically storing the solar energy into chemical energy and put it into a tank. When you want to use that in the evening, when you actually do not have sunshine shining on it, you can just flow this electric liquid back and discharge it on the electrode. You can get electricity out. Right? So basically, you actually skip the step of generating electricity and send that electricity through a wire to a separate device. You can actually do that in one integrated device. Okay, that's actually basically the idea we had. Right? So this is actually the first dimension we had, where at that time still learning how to build good flow batteries. This is actually the clumsy first battery we built. It's kind of big. It's about a couple inch large. And then this is actually the first couples we used. These are now vanadium and metal oxide, they're actually organic materials. That actually has been actually under a lot of studies in the last few years. When flow battery come into fashion, people are really interested in this. The idea is actually that people think in the long run, if you can make organic flow battery really work well, this will be cheaper than vanadium. Turns out vanadium is actually not a very cheap metal. It's actually quite rare, and limit the cost of the vanadium flow battery. In the end, actually, you can be paying quite a bit if you use a lot of vanadium, right? So this is actually basically the initial demonstration we did, right? So in this one, we first learned how to cycle the full batteries. This is the typical way people cycle the full battery. You charge up and charge down and see how it goes. We actually can build reasonably efficient flow batteries, just like what people showed. Now this is actually our solar flow battery. We call that solar flow battery. We can now charge up the redox couples and actually discharge it. We can do it several cycles, okay? And then we have to actually define a new efficiency matrix, okay? So we call that solar to output electricity efficiency. So what that meant is that we're looking at how much solar energy input we have versus how much energy we get out as a form of electricity delivered by the battery, right? So it's actually kind of like a round trip efficiency, a time shifted energy, right? So the typical solar cell, you get that efficiency is that moment. If you don't use it, it's wasted, right? So in this case, we can store it up, put it into a battery, and use it anytime we like, and then that whole round trip for the first cell we built is about 1.7%, which is not very high, but we were happy we got it working. It's actually the first try, right? So in fact, I'll show you actually now we're actually quite a bit better than that one, right? So now this is actually the new one will actually come out. Actually, in fact, this paper will come out on Thursday. I think there'll be some news on it. Actually, we've already written out the news story for UW News Office. And this is actually the new device we have. In this case, we really dramatically up the game. We actually try to push really hard. We get the most efficient solar cell we can get our hands on, which is actually what you call triple junction 3-5 tandem cells. Actually, they give you very high performance. And again, actually, I forgot to mention, all of this were in collaboration with my colleague in KAUST, Zhihao He, who actually can make this and modify them, actually supply it to us. So now with this high performance cell, because actually the voltage you get out of this cell is actually a lot higher, we actually can simplify the device. We now just have one electrode. We don't have two electrodes anymore because we have enough voltage to drive the complete charging and discharging of the device. Okay, so now one more thing we realized and want to emphasize in this paper is that, in fact, this device can be operated in all three different modes. You can still operate it as a traditional flow battery if you just forget about the photoelectrode, of course, right? But then you can actually operate it as a direct solar cell if you want. Okay, you can just bypass one of the electrodes and just cycle the redox couple, just like the way you do in the traditional so-called regenerative PV liquid junction solar cell. So if you don't want to store the energy, you want to use the electricity during the time sun is on, you can get that out, no problem whatsoever, right? But now the more unique thing is that we could actually now store, charge up the batteries and actually store them and discharge them. Now, with this one, also we have to find better redox couples. In this case, we found a published paper a few years ago where they have a reasonably high voltage redox couples. It turns out it's key to actually make this work better is actually have higher voltage. The solar cell we have a much larger photo voltage, and we have to find higher voltage to fully utilize the voltage we can get out of the solar cell. This is the best one we could find at our hand. We now have better ones, but this is actually what we put in the paper, right? So with all of those, turns out with all of this and with a little more efficiency optimization, we actually get now 14% efficiency. So this is actually, again, a round trip efficiency from solar light in electricity you get at the end, right? Which is actually the highest one reported for any integrated solar plus storage devices. Actually, this is why I hope actually this will catch some attention. This will be interesting news, right? So this is actually where we are on the flow battery. So again, very different ideas, and but it involves electrochemical energy conversion. But now the goal here was not to generate chemicals and generate fuels, but rather to actually figure out a way to store the energy and then deliver it efficiently as electricity later. Because in the end, I would say electricity is still quite desirable, right? So people want electricity, so how do you actually do that and do that in a large scale, right? So now actually this is probably the final slide. There is actually a philosophical question I ask, for this kind of flow battery, why should we care? Who will need it, right? So and actually I've been talking about this, in the community for about 2 years now. I got all kinds of questions, so I've been thinking a little about it, right? So in a way, I felt like these kind of integrated devices compared to separate ones, PV solar cells plus, separate large-scale flow battery, which both are happening, right? Both are real. Where is the benefit? The benefit is that is integrated devices that is actually smaller scale and hopefully more efficient, hopefully cheaper if we do the game right. If we play the game right, we can make it cheaper and more efficient. But I think the compact integrated device will be useful in the setting of remote, location, standalone operations, where basically this is actually a chart of, you see, I think actually we probably don't need it in big cities, but if you go to remote places of, in the desert, in Africa, in rural India, rural China, in Ireland, in remote places, where having an integrated standalone device would be very useful. Right? Again, actually, if I would actually try to sell this to DoD, I think maybe this would be useful for them. If you set up a radar station in remote island in the middle of the desert, you don't have a grid, this will actually allow to operate something directly. Right? So that's sort of how I think this will actually will likely come in, sort of like the middle ground between the really small device and really big devices, where you want remote autonomous operations. Okay, so I think with that I will probably stop. It's actually already 50 minutes. Okay, and I think again, as I said, I apologize. There's a bunch of different ideas, but this is, I guess, the part of the fun I'm trying to do, trying to see how do I articulate, how do I think about these problems coming from the renewable energy and several different directions, but they all, in a way, are serving an idea of how do we actually push renewable energy to the next level? How do we solve the problem of storage? How do we actually utilize the increasingly cheap electricity, increasingly cheap electron to do something interesting, to something of value? Not just we feel good about it, but also actually will compete economically, in a meaningful way. Right? Because there are things that we feel very good, but if you look at economics, they will not take off, at least not take off in the short term. Right? So I hope some of them might be interesting, and I'll stop here and thank my students and thank the people who pay for the the research, and I'll be happy to answer any question you might have. Okay, all right. Okay. Yes.
In addition to finding a storage system for solar power, do you think we'll have to upgrade the grid system that the United States uses?
Sorry, I didn't catch it. Okay.
The grid system that we use to transfer energy between one city to another. I think that'll be something that'll have to progress as well in the future.
Oh yeah, certainly this is happening. This is like a lot of research on grid as well, right? So how do you make them smart? How do you make them responsive? Okay, so how do you make them stable, right? Because when you actually add more component where it was hard to predict, they tend to be more unstable, right? And that's just far from my expertise, so I don't know much about it, but I know it's happening. I believe maybe someone on campus were involved in that as well, right? So the E department, maybe there's someone doing the modeling and stuff. Yes.
What kind of volumes of liquid stored?
For the flow batteries?
Yeah, what kind of volumes do you have now, and are there obstacles to scaling that up?
Yeah, well, this is actually the real size, right? This is actually this is a size of a a semi-truck or something, right? So this is actually the size we're talking about, right? I mean, you can calculate what is the solubility of the redox couple you can make in the water, and you can calculate how much energy you can put into that redox couple, the electron volts you have and the concentration. You can do that calculation, right? So this can be a very large volume, right? But again, the idea will be that this is actually still cheaper than building on the solid-state batteries, where you have to basically the problem with solid-state battery is all of the material are scalable, right? You not only have more electrodes, more lithium cobalt oxide, more graphite, you have more lithium, you also have the more membrane, more current collectors. And also, if actually the silicon battery are so-called jelly roll, they roll into a little thing too. So even if you have a big battery in your car, if you go into each component, each of them is no bigger than the one you have in your laptop. Each of them comes from the size where it's a micron size control of the dimension. So the manufacturing process is actually not very easy to scale. This is actually why Model 3 is not being delivered on time, because they just cannot make the battery fast enough, right? There's a lot of complexity in making it more scalable, cheaper, more reproducible at a large scale, right? So they saying, once you have the power unit, if you want to scale up, you just have a bigger tank, more liquid, right? That's actually the idea. Right?
So that's a 2 megawatt hour.
This is actually about this is a power unit, right? 2 megawatt hours in terms of how much power you can get. I think the total storage capacity is about 8 megawatt hour. So you would charge 4 hours, you get 8 megawatts hour. Right, megawatt.
And that could store 8 megawatt hours.
In the full 4 hour charging, yeah. Mm-hmm. If you charge it for 4 hours, you get about that much, yeah. Which is actually, if you think about it, it's still not a lot, okay? But it's already a lot more than what other things you can do. Right? As I said, I haven't tracked the news. I think they were saying last year that sometime in the next few months, later this year, there will be a 200 megawatts hour unit, 200 megawatts power unit in China that will be deployed. And in fact, in reality, on the flow battery, the commercial flow battery, Australia is really ahead. They have a lot of group in Australia, and then I think the Chinese are catching up quite quickly in the last few years. And I think US, I think there's some company that spun out from PNL, Pacific Northwestern. I know actually are doing pretty well. And there are actually a lot of activity going on to actually commercialize this. Yeah. But right now, most of the commercial ones, the big ones, the ones that are more ready to deploy, are still based on vanadium. This is actually the one that works very well. It's just that, as I said, vanadium is actually still quite expensive. There's a cost intrinsic to the cost of vanadium. Yeah. Yes?
Are there any obstacles to making this a mobile power plant equipment and vehicle?
Well, as I said, right? So because when you do flow batteries or my solar flow batteries, it's just more complex, right? You have pumps, you have liquid, you have several different containers. So I think to make them small, usually they won't be competitive. So this is why I'm thinking. My personal belief is that automobiles and mobilities, batteries for cars, probably still lithium batteries or some other solid traditional batteries. But beyond that size, I think eventually this will be. At this moment, it's not clear. There are people who say, I don't believe in flow battery. I mean, remember, Tesla, again, are selling solar walls, right? They have a product, household can buy a battery pack, put in your home, you can do that. Right? So, I don't know. I think maybe at that scale, it's still okay to do lithium battery. But if you talk about megawatts, you talk about utility scale, I think it's probably a bit tricky. Right? So again, for my solar flow battery, I believe if you go to extremely small scale, probably won't work either. Because in fact, we see that, right? If you drive down the highway, sometimes you see signs that are driven by solar panels. You probably see them already. Actually, I remember one of the camping sites in the state park in northern Wisconsin have one of those. You just have a lead acid battery at the bottom. You have a small solar panel. I mean, if you want to just implement at such a small scale, it probably doesn't matter either, right? Because these are readily available. The economics of scale is such that in the short term, it's hard to beat this commodity product like this, which is that acid battery. But if you go to a slightly bigger scale, but then the integration having the solar flow battery like what I show will probably show, right? But exactly where that value will cross over, I don't know, right? So I haven't tried to start a company yet. I'm telling myself if I get a 20% solar flow battery, maybe I will, but at this moment, 14%, I don't think people will be interested. Because why? You get the silicon solar cells about 16, 17%. The full battery can be built fairly efficiently. Right now, at 40%, we're just barely talking. I think this is probably the paper that will get some people start to look at what I'm doing. But for starting a company, I have to beat an easy solution of silicon solar cell plus a real full battery. If I cannot beat that, I don't think there's any hope of starting a company. Yeah,
I mean, it's an issue of the duration of storage, right? Like how many hours you can charge and discharge, where like lithium-ion batteries are really good at kind of shorter term charging, discharging, but for a really long-term storage needs, you might go to a flow battery. Yeah.
Not quite. Okay, so I would say this is still about the total capacity. Okay, there is an issue of long duration charging. Okay, which actually there is someone who are pushing this. I believe actually DOE had a report on this, and I think there's probably going to be some grant on proposal call. How if you want to actually store some energy and store it for like months long, okay, a few weeks. There are actually different side of challenge when that happens, right? But I think where I believe where flow battery helps is really the total energy amount, right? The total capacity, okay? Because right, if you want to use lithium battery to do this, every mole electron you get, it means you have to have another mole of lithium cobalt oxide. There's another gram of the electron material, another mass of the lithium battery. That thing will just keep adding, like cost will just keep adding, right? You have to come with it, the membranes, the collectors, all the packaging, and also get bigger and bigger, the controlling the heat, you don't want to run out, you don't want them to explode. All of this actually just get crazier and crazier, right? So when you get bigger, the scalability get very problematic. For this one, in theory, if do your game right, you have the same power unit. If you do not mind waiting, because this is actually why I'm saying it's not about time. You want to spend like 3 hours or 4 hours or 10 hours turn over this whole tank, then you can have the same unit. You just have to have a bigger tank. You turn over more chemicals, you have more storage, right? That's actually where the benefit shows, right? So this really is scalable. I think the scalability is actually a big part of actually why the flow batteries are more attractive in the large scale devices, I think, right? If you actually do really short, actually this is the other problem. Go back to the grid idea. in fact, actually, one argument I always make is that this is big enough problem that I think I argue a multiple solution should be worked on, right? If you want to just even out the second or minute level of instability in the grid, in fact, the better ones supercapacitors. Those are a lot powerful. The watt you put out, is actually very good, but the total storage density is actually, total storage capacity is very low, right? You use that to even out, the very short term, glitch. You probably use lithium battery to even out, 10 minutes, 20 minutes, and then for the day and night differences, you use this. Right. I think I don't think this is actually a winner takes all kind of situation. I think it's it's sufficiently big, a sufficient complex problem. I think all of the above should be worked on. But you have to think about each of those where they fit, which part of the game they fit into. Right? And again, as I'm trying to do for the flow battery, it's a new thing, a comparatively new thing. But I'm sure people will say I don't need it because we already have PV plus flow battery. So where do I need it? I think there's a niche for this. And the niche is actually what I'm trying to articulate. I'm actually trying to learn how to to articulate this niche. Yeah. Yes.
Have you integrated the cost of this flow battery to a PD installation to figure out what the net watt per watt cost is?
I didn't. Let me clarify and make sure I understand exactly what you're asking. Right? Are you saying? If you would, are you talking about my device, the integrated ones? Or are you talking about just a PV cells plus a flow battery separately? Okay.
PV costs, you said earlier, right now are reduced to about $1 a watt.
Yeah, we just cross over $1 a watt. Yeah.
I suspect that doesn't include the capacity factor.
No. It's just like you put it on. This is actually
okay,
together.
So, so now integrate the cost
of
this
okay. I see.
with that $1
Okay.
per watt. And now what are you at? Dollars per watt,
okay.
including the storage, to get up to essentially 100% capacity.
Yeah, well, that I guess I haven't done that myself. I haven't seen the number, but I'm sure maybe someone have estimated, right? But the matter is actually that really in reality at this moment, at least in the U.S., we're not at a level. Despite the very fast growth of the renewable, the solar and wind, we're still only a fraction of a percent, I think, at this moment. We're getting close to 1% now, okay, due to the very fast growth, right? So in US, we're not at the point that this will be completely that. But in some countries, like I think Denmark, Netherlands, and Germany, there are, I think Denmark is about 10% renewable, if I remember correctly right now, okay? So for them, really, this is a present issue. For us, this is an issue that will come up, right? If we don't actually figure out this, it will be a issue. It will basically cap the ceiling on how much you can deploy in renewables. That's what I'm trying to say. Right? But how much cheaper it has to be to allow you to go 100% solar? I don't know. I suspect probably that won't happen because I will be very happy to go to 20, 30, 50% solar because before we finish the petroleum. Before we completely dig them out of the ground, I think in the long term, in the short term, they will still continue to be quite inexpensive. To beat them in all of those occasions, I think it's going to be very hard. Right? So in fact, the same thing. Actually, people will say, particularly the natural gas power plant, it's very easy to turn up and turn down. So there are actually arguments people say we have to keep enough number of them to counter the renewable because when your son got collie, I can just turn off my knob on the gas power plant, so I can compensate for the loss on the solar panels we have somewhere else, right? So I think this is actually the level of the game that I don't worry about too much myself, but I think these are the things that you have to think about, right? Again, I don't think it is that renewable will take care and get rid of all of the traditional powers. I doubt it. I think in the foreseeable future, if we can grow renewable to 10%, 20%, I think that will be the tremendous success of the research community. People like me will be really happy. But together, I think we need some of these new things we need to work on. In fact, actually, interestingly, people didn't seem to be that interested in the biomass part. Is that right? How many of you work on, I think you're John, right? I think we might be John Rock, right? Okay.
No.
Okay. Okay. Yeah. How many of you work on, biomass conversions here? Maybe not many. Okay. Maybe yeah. I guess you're good. I know. Any question about the catalysis and the biomass conversion part? I'm hoping to get some feedbacks here too. Okay. Sounds like maybe not. Okay.
Well, I have a question.
Yeah.
I don't know if you want to talk about the comparison of these catalysts. Well, you presented them kind of in isolation.
Yeah.
I don't know a lot about just direct electrocatalyst,
Yeah.
heterogeneous electrocatalyst,
Yeah.
HMF oxidation.
Uh-huh.
How do these compare relative to, say, lithium oxide or some noble metal catalysts
Yes.
and other things?
They are still worse. They are still quite a bit worse. Okay, but I will be honest. They are still quite a bit worse, right? So actually, I think at this moment, I will still not convince Economics to do this. Okay, for sure. Because if you just take ruthenium or platinum and just do a thermal, the typical.
No, forget the thermal. I mean,
Just electrochemical, right? Yeah, electrochemical. I think we're still maybe about 500 millivolts away. Okay,
from existing precedents with ruthenium?
Yeah, with platinum, palladium type of catalyst. Okay, so for both HMF and I believe actually Glycol have even more precedent than HMF. I think I've seen report that where the comparable reaction will happen. Okay, right here, right? So the comparable reaction will happen. With this reaction instead of happening around 1.1, it will probably be 0.5 or 0.6. Okay, so or at least 500 millivolts. I can't remember exactly the number, but there's at least 500 millivolts, maybe even 6.
Which catalyst?
I think actually one of the ones that reported I've seen is I think platinum bismuth. That's one supposed to be one of the good ones. Okay, there's a bit of research going on electrochemical oxidation of glycol now, maybe about on the order of 20 papers or so. Most of them are bimetallic noble metals with another metal that are not so noble, like bismuth or copper or something like that. Okay. Yeah. So compared to those, we're not that. So I think in reality, obviously this is a good start in looking at catalysts that are new. But if I would build a cell like this today, I would still use platinum bismuth, right? So because the money you save by having a cheaper catalyst is probably not going to be able to counter the overall higher energy cost of the 500 millivolts because you do this day in day out and you turn on all the chemicals. Waste a lot of electricity that way. The catalyst cost at this moment is still a small fraction, I think, compared to that, right? But anyway, yeah. So that's sort of where we are. It's a good start, but we'll see if we can do better. Maybe we'll see a similar trend as people do in OER, because in OER now, I would say in the definitely the alkali environment, the ruthenium oxide and iridium oxide are nothing unusual. I mean, we have many that are better than that now, right? In the city front, still be challenging. We don't quite have anything as stable, as active as the iridium oxide. In the alkali side, we certainly have beaten the traditional noble metal oxide for the OER catalyst. So I don't know if this will ever get there, but maybe it will, maybe it won't. I don't know. Right? We have to find. That's all of the. I think this is sort of probably, at least right now, I look around, I don't see another paper on this. This is the first attempt at trying to find the catalyst that do this kind of reaction. There was actually a couple more precedent on HMF, and that guy, one of the person who did this, actually will be coming to Wisconsin to give a chemistry seminar sometime next spring. Right? So, yeah, I think this is a speaker we booked already. Yeah, but this one is actually not common. Okay.
I think we're out of time. Thanks so
All
much
right.
for your
Okay.
presentation.
Yeah. Thank you very much.